right. I'm not going to flip the screen around this time because I think that's what made the audio stop. And I'm just going to kind of talk through briefly, quite briefly, what I talked about, just so it's on record, I suppose. So we've got these things called probability density functions and cumulative distribution functions. So basically the idea is going to be that we've got a cumulative distribution function, which is the probability up to that event. So it's like a cumulative probability. And then we've got the probability density function, which when we add all those probabilities together, give us the cumulative distribution function. Now, the weirdest thing about it is that the probability density function is infinite in terms of the values for x are continuous. So in theory, every value of x doesn't have a probability, it's all 0. But what we do, because we're summing an infinite thing, if I just scroll down to the spoiler alert part, is when we're summing an infinite thing, I'll show you the Cambridge notes bit, the cumulative frequency, which is the probability that x is smaller than some value, is the integral. Okay, and that's how the two things are related. So I'll scroll back a little bit now and just going to go through it again. So what I do is I kind of talk about the idea of, well, first I say, here's a discrete one that we talked about last year, in fact. And then I kind of try to make it continuous by thinking about, well, let's say I've got a room and I divide it into 4 equal segments. What's the probability that if I close my eyes and tell you to move, you're standing in segment 2? Well, it's 1/4, right? Because it's 1/4 of the total area. And then I do it again for a circle with the chicken. And I say, what's the probability the chicken's in a circle? Well, it's the area of the circle divided by the area of the total space. So that's pi r squared divided by the side length squared, and you get that. Okay, and I kind of say in the video that this bit here is actually not true. It's not number of favorable because there's infinitely many favorable positions. And there's infinitely many possible positions. So it's about proportion rather than the actual number. And that's what continuity gives us. It gives us an infinite space, which causes problem. And then I try to kind of get you the idea of a probability distribution function by saying, if I just think about a circle, what's the probability that it's within, so the circle is 6 meters, what's the probability the chicken is within x centimeters? And I can again do proportion argument. And then I can say, well, what's the probability that's between 2 and 4 centimeters? And again, I can do a proportion argument. And you can basically build this up. And this becomes your probability density, your cumulative distribution function, sorry, your CDF. And I differentiate that to get the PDF. In the video, I also talk about the fact that the probability that it's at exactly 3 is actually 0, which is really weird because theoretically, yeah, you could stand at exactly 3, I suppose. But in practice, there's infinitely many widths away from the center that you could be. So it's like 1 divided by infinity, which gives you 0 in the limit, right? The other way to think about it is you can't stand at exactly 3. You can only stand at like 3.00000001, right? That's not exactly 3. So what we instead do for probability distribution functions is we always talk about the probability that you're in between 2 values. And, you know, and for this particular example here, what we might want to do is, you know, we might have a ruler that's accurate to the nearest centimeter. So you say, what's the probability that you're between, but actually not equal to? So you're greater than 2 meters and 99 centimeters and less than 3 meters and 1 centimeter. Well, given that my ruler is only accurate to 1 centimeter, that's basically the same as saying you're equal to 3. And that has a probability that you could calculate. I also talk about this later. It actually doesn't matter if you've got less than or less than or equal to. Again, because it's continuous. All those little singular points are actually 0. And it's only when you sum them up for an infinite amount of space that you get non-zero probability. I then talk about quartiles. So quartile is the first quarter of the probability. And given the probability that x is less than or equal to x, capital X is the random variable, X is the value of the random variable, is x cubed on 36. You just set that to a quarter and you solve it for X, okay? And then you do the same thing for half to get Q2 and 3/4 to get Q3. You can do it for percentiles as well. Like if you want the 76th percentile, you set it equal to 0.76 or something. So then we've got our definitions. So the cumulative distribution function is the probability that X, capital X, so that's the variable, and then little x is the value of the variable. So cumulative, you always start at the start of the interval, so you start at A, and then you go up to the particular point x. And we define it as capital Fx, that's the standard definition. And we know, because it's cumulative, it starts at 0, ends at 1, because we're talking about probabilities. It's continuous and it never goes down. It can be flat, you can have areas where there's no probability, but it can't be decreasing. And as I do above, you can do medians, quartiles, percentiles, whatever else. So then, as I say, the PDF we use to generate the CDF by doing this integral. So this thing here is the PDF. Now this isn't really the CDF because it doesn't start at A. But the point is, you can use the CDF if you know you started at A, but if you want a particular domain, like between the 2 and 5 meter markers you've got there, excuse me, then you can use the probability density function and integrate it. Notice it's called the probability density function, not the probability distribution function, because it's the density of the probability at a given point, not how probability is necessarily distributed. The cumulative function tells you how it's distributed, but I mean that's really a technical difference. It's not really that important. And here's just a little example. So I've differentiated the CDF to get the PDF, and then I've integrated various things and shown you how that relates to the area in 3 different aspects. Okay. And then there's some important things to know. Firstly, that the PDF is always positive or 0. The integral from A to B, from the start to the finish of the domain, is always 1. And the value of the probability of attaining a particular value is actually 0, as I talked about before. And you can kind of prove that by saying, well, what's the integral between t and t for the same t? The answer is 0 always. And that kind of tells you that it doesn't matter if you got less than or equal to or less than, you always get the same answer. It might matter in working in the questions, but not in the actual question. Okay. So then I just do a bunch of different examples. And I think with what I've said, they should be not self-explanatory, but hopefully you'd just be able to follow the writing there. And then I can answer questions on them either today in a Zoom lesson or on Thursday. So on Thursday, we'll continue on from here. So there's quite a few examples here. This is why it took 30 minutes and why it's incredibly annoying that the sound didn't record for some reason. But yes, we'll continue on Thursday. I apologize for not being in today. I don't actually feel sick, really. I just have a runny nose and a bit of a sore throat. So I'm staying away. But we've all had a test and we're all negative. So it's not COVID, it's just kidney cold, which is great. Anywho, I look forward to hopefully seeing you tomorrow. Or Thursday when we actually have class. Bye.